you will talk about systems of points in digi categories.
Thank you. So I thank Mauro and Tony to invite me. So first, this is a joint work with Bertrand Cohen, and most of the ideas are from Bertrand. And so, what is because the title "System of Points" maybe it's some strange stuff, and the idea is the following: if we have X, which is a variety, over K, K is a field of characteristic 0. So we can construct T, which is the dg category of perfect complexes on X. And one way to make a non-commutative geometry is to say, instead of consider variety, we can consider dg category, and to a variety we can associate this dg category and say to make geometry on T. But in fact, once you have T, you cannot reconstruct X. And for instance, you can have different varieties which have the same dg category of perfect complexes. So if we want to reconstruct the variety from the dg category, we need to add some structure, and this structure is what we call system of points. So this is an explanation of the title. The system of points will be some structure on a dg category to reconstruct variety from the dg category.
So this is because you don't put monoidal structure on perfect complexes.
No, but you can have X and X prime which are different with the same dg category.
Yeah, but the monoidal structure, the exact.
Without the monoidal structure.
Yes.
Yes. Because there is a result of.
Reconstruction.
Yeah. So first, I make some result about dg categories. So maybe one. dg categories. So I recall just that the dg category is a category enriched over the category ck, which is the category of complexes of k modules. Yes, in the most part of the talk, I just need k to be a ring. I will need K to be a field of characteristic 0 later. And so if T is a dg category, we can define the category of T-op modules, which is the category of dg functors from T-op to ck. For instance, if we take T-op, which is a category associated to a dg algebra B, which is a dg algebra over K. So the category is a category where there is only one object, and we assume that by definition, T-op, which is the complex of morphism, of endomorphism of this complex is B. Then in that case, we see that the T-op modules are exactly the B dg modules. And this is a generalization of notion of modules. Now there is on ck, there is a structure of category of model, as a model structure. And in that case, we can deduce from this, we deduce a model structure T-op mode. And now we define T hat, which is called sometimes ant of T-op mode, as the DG category whose objects are the fibrant and cofibrant objects in T-op mode. In fact, as any object are fibrant, we don't use this condition. Just this is the DG category of cofibrant object. And now, to any DG category, there is a genuine category which is associated to the DG category, which is called the category between brackets. And this is a general result that this category of hand of T-op module is the categories, the homotopy category of T-op mode. Now we have, in the case of enriched category, we have also enriched Yoneda functor. So we have an enriched Yoneda functor from T to T-op mode. And it is very easy to see that any representable object in T-op mode is cofibrant. Then in fact, H go inside T8. And now there is maybe another condition we want to add. First, we see that T hat, if we consider this category, the genuine category is triangulated. And in fact, you see the category T may have very few objects. For instance, in that case, the category has only one object. And we want to replace T by a category which is triangulated or stable category, if you prefer to work with infinity category, because there is also an infinity category version of all I explained there. So this category is triangulated, and in fact, we have a map now from T to this triangulated category. And the image, in fact, is in the compact object of this triangulated category. It's not difficult to see that. And now we say that we can also see that this one is a category associated to the category of perfect object in T hat, and an object E in T hat is perfect by definition if it is homotopically of finite presentation. So this is some finiteness condition, and the fundamental result is the following. The perfect object in T hat, this DG category, is, in some sense, the closure of T is the smallest full DG category of T-op mode, which is stable by coordinates. I think that is all what I mean. And if you consider at the level of the triangulated category, this is the triangulated hull of T. So all this is to replace T by some category which behaves better, which is T hat C or T hat P if you are at the level of the genuine category of the DG category. And all the results we have on T, in fact, are result on T hat P. Okay, so now maybe I can give you some definitions. We say that T is first triangulated if in fact T is isomorphic to T at P. Maybe we need compact as a compact generator. If there exists a P, which is a DG algebra, such that T at is isomorphic to B op at. And now, maybe which is more important, so this is 1, 2, 3, we say that T is smooth. No, yes, maybe we can begin by smooth. If we have, if T is as a compact generator, and so this we have this isomorphism, and we assume that B is perfect as B tensor B of module, and for is proper, T is proper if T as a compact generator and B is proper, is perfect, sorry, is perfect in CK, and for 5, sorry, T is saturated, and this will be if T is triangulated, smooth, and proper. And in fact, we are going to consider only saturated DG categories now. The reason is that if we take X, which is a smooth and proper variety, the DG category of perfect complexes is saturated. So if X is smooth and proper, this implies that T, which is category of perfect complexes, X is saturated. So we will consider only saturated DG category. And saturated DG category are very important objects. In fact, we can say that the DG, the saturated DG categories are dualizable objects in the category of DG category, in what we call DG type. And if we consider two DG categories, T1 and T2, which are saturated, then we have an internal ohm, which is the DG category ohm from T1 to T2. It is saturated. And in fact, this is isomorphic to T1 op tensor T2. We take the at and we take the perfect object in this one. And one very important property of DG, of saturated DG category, is the existence of Serre functor.
Sorry, quick question. In the thing you're just erasing, is
Okay.
the perf thing stable by finite colimits? No, not just arbitrary.
Yes,
It should be
by what I said, it was TP perfect?
T perf, yeah.
Yes, finite.
Okay.
Yes. In fact, you take cone, retract,
Right.
and the shift. Okay, so we have a serre functor. So if T is separated, there exists ST, which is a serre functor, which is defined by the following. TAB, the dual of TAB is T of B STA. Maybe I will say that if T is a DG category, as I told you, T is the enriched over CK, and this is the CK of morphism, the morphism from A to B, which is a complex, which is in CK. And this means the ohm in CK. So, okay, I think that on DG category I don't need more. And now maybe what is the most important object in this talk is the moduli of object in DG category.
Is the serre functor necessarily an equivalence in this situation?
What?
It's necessarily an equivalence automatic.
What is
The
where
serre functor.
the existence?
The serre functor, whenever it's saturated, there exists a functor like this, which is also an equivalence.
Yes.
This-
Yes.
Okay.
So this, the idea is the following: we take T, which is any DG category, and we want to find a space which classifies the object of the DG category. And as I tell you, the category, the DG category, can have very few objects. So this is the reason why to define this stack, this will be a stack which classifies the objects. We will consider not T, but in fact the triangulated closure of T, or the style closure of T. So what it is MT? So MT, it is a derived stack. So we can see that it is a functor from the category of simplicial commutative algebra over K to simplicial set. Or, for instance, there we can use, we use the characteristic 0. This is the category of commutative DG algebra, CGA, okay, in non-positive degree. So this is a functor. And to A, what is the image? One way to describe this, we can say that MTA is the simplicial nerve of the category of equivalence of T tensor A modules. I'm not here on T off. Whose the underlying complex of A module is perfect. This is what we call pseudo-perfect module. T op EG modules. But the first remark we can make that if T is saturated, and it is not not easy to see that, but it's very convenient. If T is saturated, in fact, pseudo-perfect is equivalent to perfect. And it is more convenient to consider perfect module than pseudo-perfect module. So this is one reason to consider this, this assumption. So there is another way now to describe this stack. We can say that MTA, by definition, is the classifying space in the category of DG category of T op to A perfect hat. So as A is a CDGA, you can consider A as DG category, and this is the DG category of A modules which are cofibrant and perfect. And
so if your T has a compact object, it has a B. You wrote B before.
yes,
This T hat here is B.
yes,
also has
this
S
is
here.
the same that Hayhock modules. You take the cofibrant object, which are perfect as this is a complex on CK, and you assume that there are perfect as complex on CK.
No, my question is, in that case, what is this moduli function?
In the case of?
In the case that you have this B,
I mean, in the case of where T is a perf
the
on
T
an
hat is
variety,
equal to B op hat.
but B is what?
B a DGA. Yeah.
But is it?
No, but
like, so to give you intuition, I think if X is a variety, and you take
X
as
is a
T,
variable.
yeah, and you take T to be perfect complexes on X, then this is the moduli stack of perfect complexes on X as a stack. So it's a map from X to perf the geometric type. Is it?
No, I don't understand. In any case, as T is saturated, this is exactly the same. In fact, as I told you, this only depends on this category. And if T is saturated, this category is a category which is equivalent to a category associated to the DG algebra. So in any case, what we obtain is something you can think that T, in fact, is a DG algebra. In fact, you can replace. You have T who has a DG. We have the compact generator.
The map is taken in DG categories, but up to Morita.
I think that there is no difference in that case, but
yes, because,
in that case it's the same.
Because you completed.
Yeah.
Your question.
So it's not easier to consider the case of a DG algebra because it is always equivalent to the case of a DG algebra. And another way is to see that this is a classifying space of map from 1, I will explain 2. I will explain that 1, in fact, this is a neutral object. This is the DG category associated to the A, which is K, which is the K in degree 0. I don't know how to call that. So this is map from T tensor A hat and pseudo-perfect, but in that case, this is perfect. So this is the description we have there, which is the nerve of equivalences of, I don't know, yes, maybe there is no up. I don't know if there is up. I think that there is no up there. So, for instance, if we consider empty K, this is the nerve, in fact, of equivalences of T modules. So what we have that the pi naught of this simplicial set is the set of equivalent classes of, so I don't know if I need up or not. Depends, maybe. So for any x now, we have the pi 1 of mtkx, which is in fact the automorphism in T from x, and for pi 1, and pi I, which is x1 minus I of x to x. So this object, maybe the very deep and difficult result is the following. If T is saturated, in fact we don't need saturated, we need only a finiteness condition, then MT is locally geometric and locally of finite type stack, derived stack. So it cannot be a geometric and a stack and a finite type because it's too big. But if we restrict the amplitude of the module to consider, it is a finite, it's a geometric or finite type. And in fact, MT is the union of all these substacks. We are open substacks, and we say that it is only locally geometric and locally of finite type. Another way to describe this stack is the following. As I told you, if I take X, which is a variety, I can associate to X the DG category of perfect complexes on X. But in fact, you have this functor for derived stack. So we have a functor from derived stack to DG category. We send a stack F to the category of perfect complex of F. And in fact, MT is left adjoint, so the functor T, which sent to MT, is left adjoint of this functor. But in fact, this is not exactly, because we have to consider T op. So if we want to write this correctly, what we have is that map in the category of derived stack from F to MT is the same as the map in DGCAT from T op to LP of F. Okay. So in fact, what we are going to consider is not this derived stack, but we are consider the truncation. This is the restriction of this stack, not to the category of commutative algebra. So now what I will call MT, in fact, the notation FT is what we call the MT0, the T0, the truncation of MT. This is the functor restrict to the commutative algebra over K to simplicial set. And to A is to say, consider the Mer's MTA of equivalences of T of tensor A modules. So, as I told you, we will consider MT to construct now the variety X from the category T. And in some sense, we will see that X will be an open substack of MT. This is what we want. We consider T, and we want to find X as an open substack of MT. And as I told you, for the same T, we can obtain different X, so different open substacks. And now I will introduce what are the new data we need to construct X. So the first one is what we call a T structure.
So that MTA, that's simplicial set is basically like you look at perfect complexes on so if T is coming from a smooth and proper X, then that MTA will be like the perfect complexes on T restricted, X restricted to the, or X base change to spec A, or?
No, MT of A, it's not very easy to describe because it is a this is a perfect complex on, I don't know exactly, but if you take K, you obtain exactly the perfect complexes on X, on the variety.
Then you don't, so for a general A, you don't get the perfect complexes on the base change?
No, I am not sure.
For general A, you get pseudo. No, like it depends on. Sorry, what's the question?
So let A be smooth, then do you get
A or T?
So T is smooth and proper, so it's coming from.
Yeah.
Let's say that T comes from a smooth and proper variety X.
Okay.
Then my question is whether MTA is the same as the perfect complexes.
Perfect complexes
On the base change, right?
Yeah.
Okay.
In any case?
Yeah. So like when T is a perf of X, then MT is a map in the right stacks from X to perf, which
Yes.
is M of 1. Yeah, so
Yes.
yeah. So when you take A points, you use the universal property of the mapping stack, and you see that it's perfect complexes on the base change.
Neat. Thank you.
Okay, so what is it? So you know what is a T structure on a triangulated category. And by definition, the T structure on a DG category T is a T structure on the triangulated category associated to T hat. And maybe one of the points is that we don't consider a T structure on the compact object, but we need to consider T structure on all these categories. And maybe if I have time, I will explain why we need to do that. So to define a T structure, in fact, it is the same that to obtain a T at, maybe I do that. Wait a minute. So non bigger than 0, so which is a full sub-DG category of T hat, which is stable by colimits. And the data of this subcategory is the same as the data of a T structure. And in the same way, we can define what is T hat non bigger than A or T hat non smaller than B. We can also define T hat with AB equine bracket, which is a no, it's a, maybe if I want to have that, it's maybe this one. So if I take the intersection of these two, I obtain this DG category. Now we can define the art. So the art is we take A and B, which are equal to 0. And if we consider now the genuine category, which is associated to this, what we obtain is exactly the art H hat of the T structure on the triangulated category, and we know that this is an abelian category. Okay. And now we want some property about this T structure, and maybe I will go quickly because I don't have a lot of time. First, we say if we consider A, which is a K algebra, we can define T tensor A, or maybe T A, which is it is not exactly T tensor A. In some sense, we have to complete, but maybe as A is commutative, this is the same as the ohm from A to T. So this is not a good definition. In the same way, you have TA hat, which is the ohm from A to T hat. And now, a T structure on T induces the T structure on TA. One way to say that is, for instance, by looking at the following diagram. We have a natural map from T hat A to T hat. Here we consider T hat non smaller than 0, and we say that T at A non smaller from 0 is obtained by the Cartesian diagram. And this, and another way, we can define also the negative part of the T structure. In the same way, TA at negative part is a full subcategory, DG category, generated by the object which are E tensor A over K with E which is in the negative part of TA. And now there is a claim that, in fact, this defines a T structure on TA. So we can define now a stack. Now we have T, which is DG category with a T structure. And now we can define MTAB, which is defined by for any A, MTAB of A, in fact, is the sub-simplicial set of MT of A, so the full sub-simplicial set of E with E belong to TA. And maybe there is a lemma, which is not too difficult, that in fact MTAB, which is defined by this way, is in fact the stack for the entire topology. And in fact, it is an open substack. No, in fact, the condition, the first condition we need is this one. Maybe the T structure is open if MTAB in MT is an open substack for any A and B. Okay. And now we need another condition on the T structure. We say that the T structure is perfect if
So can you give an example of a non-open T structure?
no, I don't have any example. But maybe you can construct, but no, I don't have an example.
An example of the structure,
But it is not open. I never look if there is an example. Maybe if you want to construct something very bizarre, you can obtain this. But
Yeah, because so for if you start the smooth and proper variety, then it's open.
yes. If you take a smooth and proper variety, and you consider the T structure, we will consider in the what follow. We have all the properties. In fact, this result is not very interesting in the sense that we put all the conditions we need to obtain the reconstruction theorem.
Mm-hmm.
So all this is what you have when you consider the T structure defined on the DG category of perfect complexes on a variety. But okay, so I see that I need another property, but excuse me. Yes, it's right. So it's perfect. If for any A which is regular algebra, we have the T structure on TA hat is compact, and say that it's compact. That means that in fact the object, the compact object, are rather the same as the object with finite amplitude. It means that it's not exactly the definition, but it's very close to this condition. That means the same to consider a compact object in TA, which is doesn't depend on the T structure, and consider an object which has a finite amplitude for the T structure. So this is some this is yes, some property of finiteness property of the T structure. And there is another condition on the arc, but it's not very important. So this is condition we need on the T structure. Now there is another data we need to have the reconstruction theorem. It was recalled so the punctual object and system of points. So we already have T, which is DG category, saturated if you want. We have saturated. And we say that X, which is an object in T, is a punctual object of dimension D. If we have the following, first, for any negative I, hi of Txx is 0, that means that the T of xx is in amplitude 0 plus infinity. The second condition is that in fact the DG algebra Txx is quasi-isomorphic to in fact the symmetric algebra over the T1, H1. The third condition is that in fact H1 is a K vector space of dimension D. And the fourth condition is that if we apply the third duality to X, what we obtain is X shifted by D. And now, why we have this condition? In fact, the system of points will be the skyscraper complex associated to a point of the variety. And this is what we want. If we consider this complex, if we consider a smooth variety with this complex, we have this property. This is the smoothness, and in fact the H1 of T of xx is a tangent space. So we find that this is a vector space of dimension D, that will be the dimension of the variety, and this is the third duality for a smooth variety. So in fact, the condition, the definition is what we need if you want a punctual object to be a skyscraper complex associated to a point. So we don't want.
So this H1 is shifted, so it's in degree 1.
Oh yes, it may be shifted because it is.
It's
1 or minus 1. Minus 1. Yes, minus 2. Yes. I always make it. So, but we don't want to consider only one point. We want to consider all the points, and all the points. This will be a system of points P. So a system of points will be a set of equivalent classes. So this is a set of equivalent classes of objects in T, such that first, for any x in P, x is a punctual object. So we want that this is a point. We want if we take two different objects, in fact, we have some orthogonality conditions. That means that in fact T, x, y is 0. And we want to have enough points. So for any E in T, E is 0, equivalent to 0, if and only if we have T Ex, which is equal to 0 for any x. So a system of points is if we take all the points of the closed points of the variety. And now, once we have a system of points, we can define a T structure for this system of points.
Is there x and y in the same dimension?
Yes, excuse me, yes. So maybe a system of points of dimension d and all objects of dimension d. Thank you. Yes, you have to fix the dimension. Now, if you have a system of points, you can define the T-structure. That will be the natural T-structure we have on the complexes of sheaves on a variety. And what are these? The definition of the T-structure associated to the system of points is that E is in the negative part of the T-structure if for any x, for any point, we have for any negative I, hi of ex, which is equal to 0. And maybe in that case, what we see that in fact any x in P, in fact, x is in the art. So I call H the art, in fact it is the art of the T-structure, and I take the trace on the perfect object. And in fact we have more, that in fact P is the class of all simple elements of the art.
So if I start with a smooth and proper variety, and the system of points is just the push forward of the skyscraper shapes at each point.
Yes.
Then the T structure induced by this is the standard T structure.
Yes. So maybe I can now give you the theorem. Just we need another property. Which is, so we have T, which is so the always saturated DG category. We have P, which is a system of points of dimension D. We have T, which is a T structure associated to P. And we assume another condition, or we assume now that this T structure, this is our assumption, is open and perfect. And the other condition that P is bounded. And what means that P is bounded? That in fact, you see the stack MT is not finite. It's not of finite type, it's not geometric. But it is a union of substack which are geometric and of finite type. And in fact, we want that P is included in this. So maybe we can say there exists U, or I don't know, N in MT, which is an open substack with N geometric and of finite type, such that pi naught of P is pi naught R. Maybe I am not defined MP, but I will. No P not. Yes, P. We can see P. It's in pi naught of N of K. Okay, and now with this property, I can give you the theorem. So first, I will define MP. So MP will be a substack of MT. So a substack, we see trace stack for the moment, which is defined by the following. for any A which is a K algebra of finite type, we define the subset MP of A as the subset of E. So E, which is, this is a subset of MTA. So this is a subset of E, which is in TA, and which satisfies the following. E is in the art of the trace structure on TA. And for any map from A to K, E tensor K over A. So this is in the art of T, and we want, in fact, this is in P. So this is exactly the object on A when we consider. This is the same if you consider a spec A, and so you consider all the closed points of spec A, and when we restrict to this point, what we obtain is the skyscraper shift. So this is first result. This is a stack, and the theorem is the following. I have give a definition for a K-algebra of finite type, and now for any A, I can write MP of A as the colimit of MP of A alpha, where A alpha is in the filtered system of sub-algebra of finite type. And now the theorem. MP is an algebraic one stack, in fact of finite type. And I cannot explain why, but in fact we have something. If I consider MP, which is the coarse moduli space associated, we have in fact that MP over, I don't know how to say, MP, the same, is in fact a GM gerbe, and MP is an algebraic space which is a finite type, separated, and of finite type. Over K. So we cannot obtain directly this space. What we obtain is GM gerbe over this space, but in some sense this is what we want. What we want is an algebraic stack, and we don't an algebraic space and not one stack. But we cannot avoid this. And now maybe I can give you the reconstruction theorem. So this theorem, this is maybe the most fundamental of all this theory. To have that it is an algebraic one stack, and to have this this structure of GM gerbe. But I don't have time to explain why we get that. And now I will give you the reconstruction theorem. You give me 5 minutes? Mm-hmm. So, as I told you, there is an adjunction between the functor L, so M, so from DG category, and the functor, we take the perfect object. So T and here N. So by adjunction, we get a map. So it's not exactly because there is a T op. So in fact, by adjunction, we get a map of DG category from T op to the perfect complexes on MT. And phi, in fact, corresponds to the universal T op DG module on MT. For instance, if we take U, which is a map from spec A to MT, so U correspond to E, which is an object in T, which is T op tensor A perfect DG module by definition. This corresponds to that. And in fact, what we have problem of notation. If I take X, which is in T, okay, it's in fact the inverse image of, but there is a problem. There is a problem there, but it's not. Okay, so I can give you the theorem directly. So we have always the same assumption: T with a system of points and the state structure, and we assume that T is saturated, P is a system of points which generates T, and T is perfect compact, is perfect open, and P is bounded. Now we have MP, we go to MT, and now we can define phi P by, we go from T op, so to M to L curve MT, and by G upper star to the perfect object in MP. And as MP is a GM germ, in fact, this is the sum of, we make the sum about around all the characters of GM. And it is, we can see that in fact the image is in the part of character 1, but in fact I will call also phi P from T op to the perfect object over MP, where the character is 1.
That's the other MP.
Sorry?
Straight up.
In the direct sum.
Yeah.
What is
You're decomposing the job in terms of the underlying space.
yes?
Never mind.
You have an action of GM, and you can decompose. In fact, it is not true because now it's true on MP. So we have this functor, and now the theorem is the following. P is conservative, and in fact it is an equivalence of DG category if and only if MP, so the coarse modular space, is proper. And so you see that in that case, from T and P and the T structure, we can recover a space. This space is not exactly the variety. What we obtain is that in fact we have germ and it is associated to the action. As I can say that, there is no if the germ was trivial, in fact, we will get exactly what we want. But there is no section of this, and so we cannot say that MP is exactly a variety which corresponds to T, because this is different from LP of MP. It will be true only if the germ. In the case where the germ is trivial. If the germ is not trivial, you don't have that. The result we would like to obtain is something like T of is equivalent to the perfect complex on a variety, or algebraic space which is separated and proper and smooth. Maybe here it is smooth, which is separated. I think it is smooth. It is very smooth. But it is the best we can obtain. And so the idea is, if you consider T, which is associated to a variety, and you consider the system of points which is defined by the skyscraper sheaves, we get exactly this, and MP is X, and in that case, we obtain what we want, right? Okay. So I will stop there.